This is Bob Capetta from the College of the Florida Keys, and this lesson is an introduction to sequences. So the notation we often use looks something like this. We can say that a sub n is something like n minus 1 over 2n. So let's make a table, and then from that table we'll define the sequence. n minus 1 over 2n. So if n is 1, we get 1 minus 1 over 2 times 1, which is 0 over 2, which is 0. If n is 2, that would be 2 minus 1 over 2 times 2, which is 1 over 4. If n is 3, we get 3 minus 1 over 2 times 3, which is 2 over 6, also known as 1/3. If n is 4, we'll have 4 minus 1 over 2 times 4, which is 3/8. And if n is 5, we'll have 5 minus 1 over 2 times 5, which is 4/10. And this typically goes forever. So a sub n is a list of numbers in order. So 0, 1/4, 2/6, or 1/3. I'm going to stick with 2/6, 3/8, 4/10, dot, dot, dot. So that's a way for us to describe that sequence. So it is an ordered set of numbers. One number follows the next. Let's take a look at another one. This time I will say b sub n equals -1 to the n plus 1 times 3 over n. So again, we're going to make a table. We're going to see what those values are, and then list elements of our sequence. So if n is 1, I get -1, n is 1 to the 1 plus 1 times 3 over 1. That's -1 to the second power times 3. -1 to the second power is just +1, so that's +3. If n is 2, we will take -1 to the 2 plus 1 times 3 over 2, which is -1 to the third times 3/2. But -1 to the third is -1, so -1 times 3/2 is -3/2. If n is 3, we'll go with -1 to the 3 plus 1 times 3 over 3, which is -1 to the fourth. -1 times -1 is +1. -1 times -1 is another +1, so that's +3 over 3. It's +1. If n is 4, we'll take -1 to the 4 plus 1 times 3 over 4, which is -1 to the fifth. And you'll start to see that -1 to an odd power is negative, so that's going to give me -3/4. So this sequence, again, an ordered series of numbers, an ordered collection of numbers, 3, -3/2, 1, -3/4, dot, dot, dot. That's how that goes. And the question is there some way for us to determine the pattern by looking at it? So let's construct a sequence and see if we can generate the rule for said sequence. So for example, if I have e, then I have e squared over 2, then e cubed over 3, then e to the fourth over 4, dot, dot, dot. What is a sub n? Well, sometimes it's helpful to add in the things that are assumed. E is e to the first with a denominator of 1. So you can see the exponents are increasing 1, 2, 3, 4. You can see the denominators are increasing 1, 2, 3, 4. So a sub n would be e to the n over n would be an example there. How about something like this? How about 1, 1/2, 1/4, 1/8, 1/16, dot, dot, dot. Well, what do I have there? What do I have there? if I rewrite this in terms of powers of 2, that's 1 over 2 to the 0, 1 over 2 to the first, 1 over 2 to the second, 1 over 2 to the third, 1 over 2 to the fourth. I would like this to be the first term I want. So when I start at 1 over 2 to the, I need 2 to the 0, but n is currently 1. So make it 1 over 2 to the n minus 1. Notice, n is 1, 2 to the 1 minus 1, 2 to the 0. n is 2, 2 minus 1, 2 to the first, etc. So looking at patterns and then constructing rules for them is something that we should be able to try to do. Now we also have sequences defined recursively, and those tend to be kind of interesting. So recursive sequences. Start that over. Recursive defined sequences. So I could start with something like this. I could say the first term, a sub 1 is 5, and then I could say a sub n plus 1 is 2 plus a sub n. And if I have a recursively defined sequence like this, I want to make a table and then use it to construct later values. So n, if n is 1, my formula here is a sub n plus 1 equals 2 plus a sub n. So if n is 1, a sub 1 plus 1 is 2 plus a sub 1, which tells me a sub 2 is 2 plus a sub 1, which tells me a sub 2 is 2 plus 5, which is 7. So we get a sub 2 is 7. Now I'm going to go with an n of 2, so I'm using the same rule. A sub 2 plus 1 is 2 plus a sub 2, which tells me a sub 3 is 2 plus a sub 2. What did we say a sub 2 was? We said a plus 2 was 7, which tells me a sub 3 is 9. Let's give me a third one, and we'll say that a sub 3 plus 1, n is 3. A sub 3 plus 1 is 2 plus a sub 3, which means a sub 4 is 2 plus 9, which is 11. And we'll just do one more. If n is 4, a sub 4 plus 1 is 2 plus a sub 4, which tells me that a sub 5 is 2 plus 11, which is 13. So what is my sequence? The first term is 5, and then 7, and then 9, and then 11, and then 13. So it was defined recursively. But we could also recognize that this is something we could have said directly. We could have said that a sub n is what? Is 5 plus 2 times n minus 1. If n is 1, that becomes 0 or 5. If n is 2, 2 minus 1 is 1, 5 plus 2 is 7, etc. So we had a recursively defined sequence, but in this case we were also able to define it explicitly using that format. Now, one of our favorite recursively defined sequences is the following. Let me say that a1 is 1. Let me say that a2 is 1. And let me say that a sub n plus 2 is equal to a sub n plus 1 plus a sub n. So let's go ahead and construct the first few terms in this sequence. So again, I'm going to make a table with n. Looks like I'm going to start with n as 1. And I'm going to write down this recursive formula. A sub n plus 2 equals a sub n plus 1 plus a sub n. So if n is 1, a sub 1 plus 2 equals a sub 1 plus 1 plus a sub 1, which tells me a sub 3 is a sub 2 plus a sub 1, which tells me a sub 3 is 1 plus 1, which is 2. Then we'll go to n equals 2, plugging 2 in that value. What do we get? A sub 2 plus 2 equals a sub 2 plus 1 plus a sub 2, substituting 2 wherever I see an n, which tells me a sub 4 is a sub 3 plus a sub 2, which is what? A sub 3 was 2, and a sub 2 was 1. It equals 3, so a sub 4 equals 3. Let's take a look at 3, plugging in 3 for n. A sub 3 plus 2 equals a sub 3 plus 1 plus a sub 3, which tells me a sub 5 is a sub 4 plus a sub 3, which tells me a sub 5 is a sub 4, 3 plus 2, which is 5. So maybe you can see the way this sequence is moving. 1, 1, 2, 3, 5. And if this continues, the next one would be 8, and then 13, and then 21, and then 34. So you can see the next term is just adding the two previous. That's what this is telling me. The next two, take the previous one and the one previous to that and add it together. This is famous. This is called the Fibonacci sequence. And there's one more that I want to show you, one more famous sequence that will lead to an important function. So let's take a look at this. This time I will say, define this recursively again. A sub 1 is 1, and a sub n plus 1 equals what? Equals n plus 1 times a sub n. So again, we want to go ahead and make a table to see how that works. What does this sequence look like? N, and then our rule here is a sub n plus 1 equals n plus 1 times a sub n. If n is 1, a sub 1 plus 1, a sub 2 is equaling 1 plus 1 times a sub 1, which tells me a sub 2 is 2 times a sub 1, which is 2 times 1, which is 2. Let me go to n equals 2, so plugging in a 2 for n, a sub 2 plus 1 equals 2 plus 1 times 2 plus 1, excuse me, 2 plus 1 times a sub 2, which tells me that a sub 3 is 3 times a sub 2, which is 3 times 2, which is 6. N is 3, plugging 3 in for n, a sub 3 plus 1 equals 3 plus 1 times a sub n times a sub 3, which tells me a sub 4 is 4 times a sub 3, which is 4 times 6, which is 24. And let's do one more. N is 4, a sub 4 plus 1 equals 4 plus 1 times a sub 4. A sub 4 plus 1 tells me a sub 5 is 5 times a sub 4, which is 5 times 24, which is 120. And you will soon recognize that this is our sequence. Fine, 1, 2, 6, 24, 120. It's growing very quickly, but you may also recognize that these numbers, 1 corresponds to 1 factorial, 2 corresponds to 2 factorial, which is 2 times 1. 6 corresponds to 3 factorial, which is 3 times 2 times 1. 24 corresponds to 4 factorial, which is 4 times 3 times 2 times 1. And 120 corresponds to 5 factorial, which is 5 times 4 times 3 times 2 times 1. But that factorial function is often defined originally in terms of that recursive function. And that will conclude this lesson.